Hi, and welcome to this conference. My name is ZAVALA, and I will present you this work called Control Based on GLRT Algorithm for Unmanned Aerial Vehicle. Unmanned aerial vehicles, also known like UAV, are versatile tools used to perform several tasks where a human pilot is not required. Nowadays, UAVs are used like supporting building construction and giving a better view of the ground. A lot of videos can be recorded while these devices are flying through the building or through the sky. The city development can also be visualized. Speaking of this, the expansion of the pipelines carrying gasoline and oil is another great task to be done by UAV. The importance of UAV is clear, and one of the most important things in UAVs are detection. There are a certain type of algorithms, and they use probability to improve the detection of targets of interest, and use a generalized likelihood radio test, also known like GLRT. This algorithm aims to detect an object floating in the sea surface without knowing its size, shape, position, and use a sequence of images. But detection is not affected by a low contrast, which is good, and makes a very versatile detector. In this work, it is proposed the study of vision-based control scheme for unmanned aerial vehicle for tracking floating objects on the sea surface using GLRT algorithm. For this purpose, it is necessary to implement control PID to a mathematical model in order to test the performance of the system control. The mathematical model considers the body of UAV like two bars joined perpendicularly at the center of mass. The motors rotate in opposite direction to prevent the UAV body from rotating about the z-axis. The three equations describing the linear movement of UAV are explained below. M is for mass, U is the principal control signal for four motors, and G is for gravity. The equations that describe rotational movement of UAV are shown below. The angles shown are related to h of the axis. The angle of rotation of the body associated with the C is called like yaw, and the angle associated with y axis is known like pitch. In other hand, the angle of rotation about x-axis is called rho. GLRT allows object detection even when the size and position are known, and it's like a universal detection for detection problems. There are two options for this kind of detection. If the target is present, there will be a return of the signal target plus the signal from the background. Otherwise, it will return exclusively the background crowded. It is used video spatial temporal patches, called bricks, to determine whether the observed brick contains the target in the presence of the random background. A hypothesis test is made to distinguish a pixel with a signal of the target plus noise H1 from others who only contain background clutter H0. The proposed vision-based control scheme is illustrated in block diagram in Figure 2. In this block diagram, you can see how the camera obtains the desired position through detection of the object that is floating on the sea surface and send a reference signal to the PID controller, which is responsible for maintaining a stable flight for UAV. Using basic sensors. The PID-based control scheme uses only 4 reference, but control 6 degrees of freedom. This type of control is named like under-actuated. That's why 6 equations were developed to describe these movements. The mathematical model is inserted in Simulink. It is software that permits the simulation of the system. The reference are linear displacement and z-axis, and the control are angular rotations and the 3 axes of the body coordinate systems. Through this rotation, indirectly the body can move along the x and y axis. In the figure 3, a small part of the image is selected. For compare it with the rest of the image, if an object is detected, then the coordinates are sent to the PID. The figure 4 is the result of the UAV and the height that was maintaining. Can be seen there was a small error. And the figure 5, the intersection of the UAV position and the object position in the x-axis can be seen. Figure 6 is the same, but now for the y-axis. Meanwhile, in figure 7, the error for 3-axis is shown. This work presented a vision-based control for tracking objects with a quadrant with a camera, and the results obtained showed a good behavior of the detection despite the constant oscillation generated by sea waves. It managed to capture the sufficient occurrence in the target within the imaging, allowing the generation of the objective trajectory. The PID control was able to maintain an appropriate tracking of the given coordinates both in the x and the y axis. However, the desired height was not reached, maintaining 9 meters when the reference was 10. Thank you very much to CONACYT and UNACAR for funding this work, and thanks for my co-workers, Dr. HUSSAIN ALAZKI, David CORTES, and Victor GOLIKOV. Good morning, good day, or good afternoon.